Welcome everybody. We are looking at some of the solutions to the practice questions on electricity and circuits. Let's do it. Okay, so let's look at question 1. A charge of 4 microcoulombs builds up on a surface. How many electrons are present? Okay, so to think about this question, we need to draw on this one, which is the elementary charge, 1.602 times 10 to the negative 19 coulombs. Now, we're after the number of electrons. So the number of electrons is given by taking the charge and dividing by the elementary charge per electron. And that calculation will give us this result. There we go, 2.5 times 10 to the 13 electrons. That's a lot. Alright, what about the next question? An object accumulates 6 times 10 to the 18 electrons, or extra electrons on its surface. What charge has the object acquired? Okay, so it's extra electrons giving you extra charge. So we get our amount of charge, amount of electrons, and we're going to multiply by the elementary charge this time. And there we go, 0.96 coulombs. How are we doing so far? Question 3. A positively charged object of 200 nanocoulombs is brought to 50 centimeters from a Van de Graaff generator, which produces a negative charge on its surface of 5 microcoulombs. Describe and calculate the force between the two charged objects. Okay, so force between two charged objects is given by Coulomb's law. There it is. So we need to identify those quantities from the information. Here is one charge amount, 200 nanocoulombs. That's 200 times 10 to the negative 9. And the second charge amount is down here, the charge on a surface, 5 microcoulombs, 5 times 10 to the negative 6. And then we have got to identify a distance between the charges, that is 50 centimeters. Now we're going to express that in meters, so 0.5 of a meter, half a meter. Now our job is now to work out what is the force, so that's calculating the F. Now to do that we need to know the value for the K constant in Coulomb's law. Who remembers that quantity? That's right, 9 times 10 to the 9. And then plug in our values. There we go. Make sure you add them in brackets into your calculator, and you're squaring your denominator there. Okay, and we get a result of 0.036 newtons. Or if we write that number in a different way, we've got millinewtons. Okay, so that's shifting decimal place 3 spots. 1, 2, 3. 36 millinewtons. Okay. Next question. But before we find next question, to describe the force, well, we have a positively charged object and brought to a negatively charged surface on the Van de Graaff generator. So positive charge and a negative charge, that is an attractive force. Opposites attract. So it's an important thing to remember. Alright, question 4. A negatively charged object of 600 nanocoulombs experiences an attractive force of 20 newtons when brought as close to 10 centimeters to another charged object. 10 centimeters. Calculate and describe the charge of the other object. Okay. So there's our first charged quantity. 600 nanocoulombs, 10 to the negative 9. And we've got a force of 20 newtons. And here's our distance of 10 centimeters. But what have I done? I've written as 20 centimeters. Okay, well, my mistake, but I'm sure you can figure that out, correct it yourself. Now, let's use Coulomb's law, and we set up the formula that's the formula. Now from that, our job is to work out what is the other charge. Calculate the and describe the charge on the other object. So we're after this charge here. So we have to transpose this formula. Well, that's done by multiplying the r squared to the left-hand side and then dividing by the k constant and charge 1. And we get this as a rearranged formula. So that's important to be able to do that correctly. Now let's substitute our values in, like so. And I've substituted 0.2 going with this value, but you can do the same and substitute in 10 centimeters. And we calculate carefully. We get some quantity like so, and then, hang on, I can shift my decimal place. This time, how many times am I going to shift it? Let's shift it 1, 2, 3, 4, 5, 6 times. So shifting it 6 times like that, what's the equivalent units I could use now? There it is, that's right, a micro. So it's a 148 microcoulombs. Okay, next question. So a battery of 6 volts is connected only to 10 watt globe. Okay. What would be the size of the current in the circuit measured by an ammeter? Alright. Well, let's think about that. Okay. What we know about the globe, it's made up of 10 watts of power. So there's our rule for power. Power is equal to current multiplied by voltage. Okay. Now, I know the voltage in the globe, 6 volts. And from that, let's work out the current. So, power is 10, voltage is 6, and the current is unknown. So I'm going to divide by 6, and I get 10 on 6, which is approximately 1.7 ammeters. There you go. Now, from that, how much energy is converted to heat and light by the globe if it is left on for 1 whole hour? Well, power is also expressed as energy divided by time. Electrical energy divided by time. So we're interested now in how much energy is used by the globe converted to heat and light. Well, electrical energy converted to heat and light is given by the power multiplied by the time of use. Now, we know that from the globe information, the power is 10 watts. What about the time? Well, the time is 1 hour, but we're not allowed to use 1 hour as our unit because the time measure is measured in seconds. So there's 60 minutes in 1 hour and 60 seconds in 1 minute. So 3,600 seconds in 1 whole hour. Okay. So 10 times 3,600 gives 36,000 joules for energy. Okay. Now, what's another way of expressing that number? Well, I've got 36,000, so I can say there 36 kilojoules. Very good. Alright, how are we going so far? Let's keep going. Now, question 6. A resistor is placed in series in a circuit with an EMF source and a switch. Okay, that's interesting. Below is an IV characteristic graph of a conductor. Okay, so this is the current versus potential difference across the conductor. Okay, is the component considered to be an ohmic or a non-ohmic conductor? Okay, well, what do we remember about the characteristic curves of, say, an ohmic conductor? Well, linear graphs in this curve of current and potential difference, they are ohmic conductors. Yes, so if you said an ohmic conductor, you would be correct. Alright, so let's continue. Part B, calculate the resistance of the component. Okay, so who remembers how resistance, current, and potential difference all link together? Well, that's done by Ohm's law, V equals IR. Now, the resistance is given by the potential difference divided by the current, but if we look at our graph, we've got current in the vertical axis and potential difference in the horizontal axis. So just by flipping them around, current on the top, potential difference on the bottom, that's equivalent to 1 divided by the resistance. And what is that going to be on the graph? That's your gradient of the graph. The rise being the current divided by the run being the potential difference. Okay, so once we get our gradient, that is the same as the reciprocal of the resistance, 1 divided the resistance. So let's work out the gradient. So we've got a run of running across the graph 8 volts of potential difference, and a rise going up to 2. Looking on the scale of the graph, that's 2 milliamps. So it's important to read the units measured in milliamps for current. 2 milliamps. So the rise over run, being the gradient, is 2 milliamps divided by 8 volts. Now 2 milliamps is 2 times 10 to the negative 3. Then we divide by 8, do that on a calculator, and we get 1 over 4,000. Now that being the result for the gradient, which is the same as 1 over resistance. So 1 over the resistance is 1 over 4,000. So what would the resistance be? Yes, the resistance is 4,000 ohms, or 4 kilo ohms. There it is. Well done. So how'd you go with that one? Okay. Let's look at question 7. So the potential difference across a resistor in a circuit is 2 volts. But it was observed that 25 joules of electrical energy was expended in 5 seconds. Okay, so now what is the amount of charge that would expend 20 joules of electrical energy as it passes through the resistor? Okay, well, that's not a very good question. I think that's a typing error, Mr. Stevens. So what we're going to do is fix this quantity. We need it to be the same as the 25 joules. Okay, so if our energy is 25 joules, then in our question, what is the amount of charge that would expend the 25 joules of electrical energy as it passes through the resistor? That's better. Alright, so what we've identified is the potential difference across a resistor. Well, that's our 2 volts, that's our potential difference. The energy, E, is 25 joules for T equal 5 seconds. So how do we work out the amount of charge, a Q, from that information? Well, we need to draw on the idea that the potential difference is the same as the energy lost, or the energy consumed by the device, divided by the charge. So charge is then, rearranging the formula, energy divided by the potential difference. Now the energy is our 25 joules divided by a potential difference of 2 volts. So 25 divided 2. There it is, 12.5 coulombs of charge. Now from that, part B, determine the current in the circuit. So current, well, current is charge divided by time. Now our charge is our 12.5, and the time for that amount of charge to flow through the circuit was 5 seconds. So 12.5 divided by 5 seconds gives us 2.5 ammeters of current. In part C, what is the resistance of the resistor component in the circuit? Well, using Ohm's law, V equals IR, the resistance is given by V divide I. Now it's important to realize this V is our potential difference. It's the potential difference across the resistor. So it's the change in voltage across the resistor divided by the current passing through the resistor. Okay, so it's the application of this Ohm's law in the context of this question. The potential difference across a resistor. That is 2 volts divided by the current, which we worked out here, of 2.5 amps, and that is 0.8 ohms. So Very can be a challenging question because part A, B, and C work out in sequence. So to work out C, you have to work out B, and to work out B, you have to work out A. Alright, let's moving on. Question 8. So a circuit has 5 ohms, 10 ohms, and 150 ohm resistors connected in series. Now this is in series to a 9-volt battery power supply. So calculate the total resistance of a circuit. Total resistance of a series circuit. So total resistance is found through the addition of all the 3 resistors. So total resistance is resistance 1 plus resistance 2 plus resistance 3. Okay, and that's simple. So that's just 5 plus 10 plus 15 is 30 ohms. Okay, and now from that, part B, determine the current in the circuit. Okay, so what connects voltage, resistance, and current together? That's Ohm's law, V equals IR. And so current is worked out by voltage, or potential difference, divided by the resistance. Okay. So the current in the circuit is then take the electric potential and divide it by the total resistance that we worked out. So it's the total resistance in the circuit divided by electric potential of 9. It gives you 0.3 amps. Question 9. Now a circuit has 5 ohms, 10 ohms, and 15 ohm resistors connected in parallel to a 9-volt power supply. Calculate the total resistance of the circuit. So this time total resistance is found for parallel circuits. Okay, given by this relationship. So it's the reciprocal of each. 1 over R total is 1 over R1 plus 1 over R2 plus 1 over R3. So there we are. We set up fraction addition. Now what's the common denominator? 30. 5 into 30 goes 6 times. 10 into 30 goes 3 times, and 15 into 30 goes twice. So we add up the numerator. There it is, 11 on 30. Now, the resistance total is now the reciprocal of that number, 30 divided 11, which is approximately 2.7 ohms of resistance. So that's the total resistance for a parallel circuit. Now from that, determine the current. Okay. Current is given by V equals IR, from Ohm's law, V equals IR, so we transpose for current. Voltage, current is electric potential divided by the total resistance now in our parallel circuit. So our electric potential is 9 volts, but the total resistance now was this, 30 on 4. Okay, dividing by the fraction, well, it's like multiplying by the fraction upside down. So 9 fourths gives you 36, divide 30, well that's like an 18 divide 15, which is a 1.2 amperes of current. Well done. So what do you think of that? That was a hard one, wasn't it? Well, one more, let's look at the extension question. So in an experiment, a student set up a circuit involving an ohmic conductor, and the student measures a current in the circuit to be 0.4 of an amp, while the potential difference across the ohmic conductor is 3.5 volts. Okay, so the ammeter and the voltmeter, they have a limit of reading uncertainty of 0.005 and 0.005 volts respectively. Okay, so we have the error in the measurement there. So let's calculate the resistance of the ohmic conductor and its uncertainty. Okay, interesting. So let's identify the parts we have. So there's current, 0.4 amps, and we have a potential difference, 3.5 volts, and we also have their uncertainties being measured with a ammeter and a voltmeter. And so the limit of reading on the scale of those devices are those quantities. And then we can represent this as error. Error in the ammeter and the error in the potential difference. Okay, so the first thing is to calculate the resistance. So again, from Ohm's law, resistance equals voltage divided by current this time. And using the quantities, voltage is 3.5 and we divide it by a current of 0.4. There it is, which is 8.75 ohms of resistance. Now, here comes the big calculation for the uncertainty in resistance, and there's our formula. So this is for a dividing formula of voltage divided current, and the dividing quantities formula, the uncertainties, become this rule. Okay, so we substitute our values in. There it is, and this gives us the error in the resistance out of a fraction of its total resistance. So all we have to do now is multiply by R, multiply by its resistance, 8.75, times the square root part. And all that in a calculator, you should be getting 0.11. So therefore, our resistance and its uncertainty is 8.75 plus or minus 0.11 ohms of resistance. What do you think of that? Well, we did it. All the best for your test very soon.